Dear colleagues, let me introduce you to the next lecture on the course of medical statistics, and it will sound like this. Statistical hypothesis testing. So, well, in order to stimulate you a little bit, here I will give you a graph that, as it were, the basis of one of the foundations of this meta are the words and statements of a well-known statistician, who is, so to speak, part-time, or rather statistics, probably part-time evolutionary biologist Ronald Fisher, that all experiments are conducted in order to give the facts an opportunity to refute the null hypothesis. That's what we're going to talk about. In other words, the result of this pilot will be a discussion of this experimental activity. And medical science is an experimental science, and clinical medicine, if it is firm science, then in general it does not stand out. It is, to put it mildly, it feeds on the achievements of medical science. Yes, medicine is a certain field that uses the achievements accumulated for it by medical science. And no one has managed to make any changes to this scheme so far, so we will work within its framework. So, well, let's discuss the goals of working with hypotheses. So why hypotheses or assumptions are put forward at all? There will be further definitions. Hypotheses are put forward due to the need to draw conclusions about the whole phenomenon, about the disease, about mortality, some other processes in nature, in biology, in medicine that are happening. That is, entirely as such a fact, yes, about the whole disease or process based on the available data about its part. In other words, we always discuss with the help of statistical methods, in particular with the help of hypotheses, certain integral phenomena related to medicine, but we try to build, or rather we make assumptions, and try to draw conclusions about them, having only a part of this phenomenon, only a certain group of patients, only a certain set of facts that are part of the whole phenomenon. Because, well, we don't have a complete set of data in this process, so it's said. That is, all patients suffering from a certain disease, there is always a risk of making a mistake. The sample study is always different. The results of the sample study differ from the so-called general population. You have already been told these terms. That is, from the whole phenomenon. Always a certain group of people only partially represents the whole phenomenon. Well, let's start discussing mistakes right away. In other words, it always means that working with hypotheses is somehow connected with the concept of error. So there are generally two types of errors. You can reject the correct hypothesis, put forward a hypothesis, test it. It was true, but we call it for reasons like, well, we call it a failed experiment, well, maybe it's not good. For reasons based on the results of our experiment, we rejected it. We're making a mistake. Can we accept the opposite? The hypothesis was not correct, we conducted an experiment, and as a result of the experiment, it was confirmed, but in fact it was incorrect. The opposite error is a kind of yes error. In other words, there are two possible errors when working with the hypothesis. And we can't avoid them. We can only do what? We can in practice, here in practice, what does statistics give us when working with errors? In practice, statistical methods allow us to estimate the probability of these errors, and thus gives. And the assessment of this probability, thus gives an assessment of the reliability of the conclusions obtained. Once again, it means that the mathematical apparatus in statistics works with the so-called concept of error probability. And having assessed the probability of error, we can transfer it well into such a more streamlined concept of the reliability of conclusions, and some reasoning, yes, that which are embedded in these hypotheses. Well, so far so. And once again, the hypothesis implies mistakes, making mistakes, but statistics give us the opportunity to measure these errors. Don't just say there are mistakes. And one more thought, that there are never infallible solutions in this situation. It is important to assess the probability of this error, and the reliability of our conclusions will follow from it. It doesn't matter what conclusions, diagnostic, therapeutic, scientific, or anything else. So what's next? Well, let's see what the error is, and immediately on some clinical example. Look, the dots on this graph are individual patients, right? We've already studied the normal distribution, right? We examine in these patients the duras, that is, the amount of urine secreted in the bag as a kind of expression of kidney function. So, this is one group of patients who took a diuretic drug. There are a lot of them. Once again, each point is one patient, and they correspond ideally to a normal distribution. That is, most patients are grouped around a certain average value, yes, 800 milliliters per day. So, it means that in another group that took a placebo, well, how to say an imitation drug. Note that the distribution is also normal, but the average value corresponds to, well, it does not amount to 500 milliliters per day. And we see right now, having built all these patients, we see, yes, well, that the drug really had an effect. And the purpose of the diuretic drug is just to increase DORs, and it has goals to increase the filtration function of the kidneys. And increase it once. And these two graphs show us a situation where there is an effect, right? That is, in a certain large group, let's even assume it's a general population, although this is also a sample, of course. But we're going to make a smaller sample now. So there is an effect, because clearly the patient has. Notice, wait, this patient has 800, and this one has 800, but they belong to different groups. But there are few patients with such diuresis here, right? Although it seems to be the same DOR. In other words, you need to be able to look statistically. You need to be able to look at the average value of the group. That is, in the second group, there are 800 milliliters. In the first group, there are 500 milliliters per day. And we say that there is an effect. In other words, these diagrams show the situation when the drug had its positive effect. Let's see how the situation looks like when the drug does not have its effect. Here they are, right? Here are some different placebos received. Everyone has different ones, as you can see, but they are all grouped around the average value, and a little big diets are a little small. This is called, as we have already discussed in lectures, called the normal distribution. In the second group, the average value in the first group, respectively, the average in the second. They both have 800 milliliters, and we say that, well, the drug is ineffective, because in the placebo group. And in the drug group, it means, well, probably it was not 800, 600 there. Well, the numbers are not important here, and the situation itself is clinically a little more complicated for you. However, you see, yes, that the drug distribution of the drug corresponds to the placebo distribution. And we say that the situation demonstrates a lack of effect. But why did I show it to you? To demonstrate what a mistake is, right? Here let's have the same situation again. We have just considered it as a situation with no effect. Let's make a choice from this group of people. A sample of just 1, 2, 3, 4, 5 people. And here, notice, from the second group to 1, 2, 3, 4, 5. But fate decreed so, yes, that these 5 people, well, not necessarily, but such a situation is possible. We accidentally pull them out, took, yes, these people, that they got into the left part of this case. Well, it so happened that we got 5 people with a small diuresis. And here we got caught. This is a rare situation, because there are fewer people here, and here we got 5 people with a large diuresis. And if we hadn't seen all the other patients, but had worked with samples of 5 and 5 with these 10 people, then of course we would have said that the drug is effective, mind you, because in the second group, we would have seen the average numbers more than in the first, right? That would be the average in the second, I say again, 5 people each. And here is the average in the first group in placebo, but in the drug for 5 people. And you and I made a mistake. In other words, the drug was ineffective if all patients were measured. But as a result of a 5x5 sample study, yes, we got, as it were, the effectiveness of the drug. Well, because the shift, you see, yes, the shift diuresis. We got it seemingly effective. Here's an error occurred. We took the wrong hypothesis, right? The hypothesis is not correct. We accepted the efficiency hypothesis. It was incorrect. Yes, in this case. In this case, yes, we put forward a hypothesis about the effectiveness of the drug, and it was accepted experimentally. But in fact, as you can see, it was not true. And we made a mistake. So, how to demonstrate another error? Look again, I remind you of the same situation. The situation globally looks like it is effective for the drug. See, yes, these 2 shift patients are coming here. But fate again played us so that the patients were 5 people in the first sample and 5 people in the second, but it's possible, yes. It's all the elements of chance that we got with the same diuresis. Here it is the average value of them, yes, you see. And we rejected the correct hypothesis. The efficiency hypothesis was correct. Based on the results of this small experiment, we were forced to reject it. And again they made a mistake, but a little bit the opposite. I don't know how visually presentable this is for you. This is a kind of demonstration of the concept of efficiency, inefficiency, and demonstration of the fact that small samples from the total number lead us to errors. These are the two mistakes I would like him to try to demonstrate on these slides. So here's a visual representation of what it's about what mistakes. So, well, let's talk directly about the hypothesis now. It means scientific, or let's call it a clinical hypothesis, although in general, of course, it is correct to talk about scientific. Well, we are also in the clinic. We will give examples there later. We also manipulate the concept of hypotheses, and, rather, we do not manipulate subconsciously, often even use hypotheses in our clinical thinking. Well, then we will use the Greek name hypothese. I don't even know how, to be honest, it sounds right in Greek. This is how I read the abbreviation in English. This is the basis of the assumption. A presumed or presumptive judgment about the causal relationship of the phenomena under study. That's it. Kind of rude. That is, here is the hypothesis that the drug is effective, or rather, that the reason for the effective increase in diuresis is this particular drug. It's a hypothesis, right? In other words, we took the drug and hypothesized that it increases diuresis there, or that the reason for the strengthening of the function of the point is the effect of this drug. This will be a clinical hypothesis, or scientifically, if we are testing a drug. So, what are the requirements of the hypothesis put forward? So the hypothesis is not invented from the ceiling, it must correspond to the facts that the hypothesis is going to explain. That is, well, some kind of hypothesis should not be taken from the air, but from previous experiments, from previous reasoning. That is, from some experience, yes, it has been accumulated. There is no internal inconsistency, that is, when starting with the formulation of the hypothesis. There should be no contradictory judgments. The most important thing in the hypothesis, perhaps the most important need, is verifiability. In other words, if we put forward a hypothesis that cannot be verified, then it ceases to be a hypothesis. It can be anything, their reasoning, assumptions of faith, and in the end, yes, but it will not be a hypothesis. A hypothesis is a verifiable statement. That is, there are tools for verification. Well, accordingly, the previously accumulated knowledge has already been generally said. With the first point, I mixed it up a little. Well, and the simplicity of the presentation. After all, the name hypothesis is short, clear to everyone. Because the more scientific hypo, it should be globally understandable to everyone who reads, watches, and participates in this kind of hypothesis testing process. So here's a scientific hypothesis. Where do we start? This is the first stage of our research. We form a scientific hypothesis. Well, here's what about the previous example. We form, by creating a new drug, we form a hypothesis that it effectively acts on the filtration function of the kidneys, and thereby increases the diurs. Once again, this is a hypothesis. We want it to be so, we assume it and start checking further. Well, let's talk about other simpler hypotheses here now, for example. So, the next stage number 2, let's say, yes. We put forward statistically on the basis of scientific, form statistical hypotheses. And the fact that a scientific hypothesis can be described by one or more statistical ones. The same hypothesis about the effectiveness of the drug can be expressed in different ways, numbers and different indicators. Filtration function of the kidneys in the form of diuresis, or rather diuresis, urine volume is just one of the indicators. Yes, kidney function. There are other indicators that can be formed in the form of hypotheses. So what is a statistical hypothesis? Well, we will continue to designate the letter as much as the first one. The assumption about the property of the general population is called, which can be checked based on the sample data specifically. Well, examples at once. The middle letter M is the average. I remind you, we determine the value, the average in the general population, is equal to some value. For example, the average temperature of a healthy person is 36.6 degrees of the church. But this is a pure hypothesis. As if it has been tested by many experiments and the experience of mankind, it is still a hypothesis. No one collected all healthy people on Earth and did not check their temperature and did not count the average. According to a certain large sample, let it be, but we have such a hypothesis, we check it, we believe it, right. So, well, for example, the average temperature of sick people is more than 37. There is also some kind of conditional hypothesis that depends on the situation. But there is also some kind of formulation of scientific or clinical hypotheses. I say again, this is a hypothesis. This is an assumption that all patients with the flu, let's say, yes, have a temperature above 37. Naturally, there is a variation, someone has, someone does not have, and so on. But on average, yes, if we collect all the flu patients on planet Earth from the general bonus, we will get this figure. We are assumptions. We will check on the part of only the sick. We're only going to use some of the patients for testing, right? So the next step is already statistical. I remind you once again, we defined a scientific hypothesis, moved on to the concept of statistical. Said that one scientific hypothesis can be written down by several statistical ones. Well, let's talk about these several at once. To work, we will need at least two statistical hypotheses. This is the so-called main or test. It is more often also called an alternative. Well, we will also give it another name, but the main thing is that we will have two hypotheses. One is opposite to each other, the main one and the alternative one. Well, for example, how can we form them in different ways? We have already said that the temperature of a healthy person is 36.6, and put forward an alternative that it is anything but equal to 30,000. But let's give it a variant of it. We can check it, formulate it. Well, that's how we formulated the alternative, using the sign is not equal. Widely taken. Wait, there may be more complicated situations. For example, two schools of doctors, some claim that the average temperature of creep patients is more than 37. They are some other medical school of infectious diseases says, there are no more than 38. Here are two alternative hypotheses expressed by two schools of infectious diseases there, for example. Conditionally, I'm an example, right? But these are two hypotheses, they are alternative opinions, right? And you can check as alternatives. But this is such a difficult situation a little bit. We are simpler, after all, it's easier to check these ourselves. So, well, and the most important rule regarding these alternative hypotheses is that if we accept one of them during the test, then the alternative one, then the main one is automatically rejected. And vice versa, if the alternative one is rejected, then the main one is accepted. That is, if we check any one of them, we will check more often alternatively, and I will say why, yes, then if we reject it, it will be automatically true. Conversely, if we fail to reject her hypothesis, it will automatically be incorrect. Yes, here it is, as it were, an alternative of hypotheses. We will work with me, and make a decision about the opposite of it, relying on the opposite like this. That's why two hypotheses are introduced. Well, we always have a choice, it's some kind of decision-making. There is a choice of the most optimal, well, from alternative sources, right? The choice is always made among alternatives, and not in some airless space. This means that the null hypothesis is important, it often acts as an alternative. The hypothesis that two aggregates compared by some attribute or several attributes, yes, do not differ. It is called the null hypothesis. And we will add a 0 to denote the letter number, yes, we will denote it as much as 0. At the same time, it is assumed, understand that when we take two groups of the same patients, then we will never have the same value for them. At the same time, it is assumed that the difference in values is really 0. In other words, we really mean differences in the general population, that if we examine all patients, we will find that there are no differences or the difference will be 0. But the difference from 0, revealed by sample data, that is, in the experiment, is random. That's what we're assuming, right? Because in any experiment, there will never be 0 differences. That is, rather, there will be no differences. But we assume in a kind of null hypothesis that these differences, if we took the general population of all people, then these differences would be absent. And the presence, observation of these differences in the experiment carries a certain element of randomness, that is, caused by some set of factors unknown to us. This is what the null hypothesis looks like. And that's what the ratio of the general population and the sample looks like, right? That is, roughly speaking, the null hypothesis is the hypothesis of the absence of differences, of any differences. We're going to say different things now, too, they're just null hypotheses. So, well, an example of the simplest null hypothesis, that is, that the average value of one group for the same diuresis is equal to the average value of diuresis in another group. So the task of the study of our research here, meaning hypothesis testing, is to use sample data to accept or reject the null hypothesis. Remember, yes, Ronald Fisher's statement that the task of any research in general is to take the null hypothesis, yes. In statistics, everything is based on the null hypothesis and using a certain sample. Either reject it or accept it and, accordingly, do something with an alternative hypothesis. This is about to be a kind of repetition of Fisher's global statement, yes, that everything is based on testing the null hypothesis. Right. Well, let's take a closer look at it somehow. So let's look at it all in more detail. So it's about mistakes. Or rather, let's clarify more about the errors. So here we have just designated a hypothesis now, so we can refer to this table, why I didn't give it earlier. There was no designation. Here we understand the null hypothesis, yes, the test hypothesis. So, what is the possibility of a situation of relations between them? This is the situation when the hypothesis was true, yes, the null hypothesis was true, the first one was true, in fact, in the general population. And this is what we did, which one we accepted, right? That is, along this axis, we have the acceptance of the hypothesis, so the truth is the correct hypothesis. Look, the null hypothesis was correct, and we accepted it. Even probably, it was necessary to make mistakes, but now I'll tell you about this alpha. This is the probability of making the right decision. This is the right decision. The right decision is number 1. Now I'm not going to tell you about alpha yet. So here is an error of the so-called first kind. Here it is more important to say about errors here. It means that the null hypothesis was true. We accepted it according to some experimental signs after the experiment. We accepted an alternative hypothesis, made a mistake of the first kind. The probability of rejecting the null hypothesis when it was true, that is, an error of the first kind, here it is written, is the probability of rejecting the correct hypothesis, despite the fact that it was correct. Well, accordingly, probability 1 minus probability equals the probability of a correct decision, right? That is, the probability of an error. Rather, if you subtract the probability of error from 1, you get the probability of a correct decision. That's situation number 1, right? But always situation number 2. In fact, hypothesis number 1 was correct. We're testing it. So we're what? And we took and accepted according to some of our own experimental steps, took and accepted 0. Made a mistake of the second kind, accepted an incorrect hypothesis. That is, the first one was wrong, yes, but we took it and accepted it, right? Rather, the null hypothesis was incorrect, but we considered it correct. It was actually true that this was a testability. It's all about the null hypothesis, about fidelity, right? That is, the null hypothesis was true, or rather it was not true, the first hypothesis was true. And we accepted 0 as true. Well, it's a little bit slurred, you see, I've already tried a minimal survey, right? We made a mistake of the first kind. Once again, we took the null hypothesis as true, but it was not true, it was actually true of the alternative one. And they made a mistake of the second kind, the opposite of these mistakes. That's the balance of errors that happens here all the time. Well, accordingly, the probability of the correct decision, when the first one was correct and we accepted it. This is the minus beta unit, this is the probability of correctly accepting the hypotheses tested here. Or the so-called power is still a criterion, well, in this department. The most important thing is that we have considered 2 possible errors in this table, their names. We will be especially interested in this alpha error. We will use it more. The probability of rejecting the null hypothesis when it was actually true. Here is the ratio of errors for everyone, and in this topic, as it were, it is told, presented in this slide. So the next concept is a statistical criterion. A statistical criterion is a set of certain formulated authors. Now we will talk about the authors. They are usually called by the names of the authors. The criteria have a name and are formulated by a certain author who justified it, proposed it, and everyone began to use it. Yes. This is a set of certain rules for using numbers as manipulations with experimental data. We often formulate it in the form of a graph. Here I am presenting a graph of a statistical criterion. It reminds me, but here it is, as it uses all the normal distribution for another purpose. Graphs of certain tables of formulas. So we will use it. Well, it is difficult to use the graph, it is more accurate, but we can present the graph in the form of a table. And we will use a table that is a kind of analog of this graph. So, for those indicating this, it is a set of rules indicating under which results of an experimental study the hypothesis is rejected and under which it is considered acceptable. Now, if we talk about the graph, which is basically this area, this central area, this area of the unpainted graph, is called the hypothesis acceptance area. That is, if we conducted an experiment, calculated a criterion according to the value formula, and substituted it here. and the value of the calculated criterion falls into this area, then we say that yes, the hypothesis accepts. And this is all close to the center. This is the most frequently occurring event. If, during the experiment, it falls into this small area of blue painted over, right? If the result of our experiments falls into an area, into this area, then this is an extremely rare case. Because it takes, notice here how much? 5%. Well, now we're going to say, or rather, I'm not even going to call the numbers. It occupies a certain small area, and getting the experiment here most likely requires us to reject hypotheses. That is, very rarely, in an experiment corresponding to the hypothesis, it will fall into this blue area here. And this blue area we will call the hypothesis rejection area. And so we are going to measure it with this error of the first kind, precisely because an error of the first kind is an erroneous rejection of a hypothesis. But we will have to determine the size of the area of this area. That is, the size of the allowable error of the first kind. Because this alpha is the area of this triangle of blue. That is, once again, most of the experiments fall into this area, or rather, their results fall into this area. But if the result of the experiment falls into a small area, this far from the center, yes, then we are forced to consider this experiment to be incorrect. Yes, a hypothesis tested in such an experiment. Well, it's a little difficult from the schedule. We'd better work with tables and formulas more in practice. In general, colleagues, why tell you all this? In general, it's not because you've memorized it. All of this happening at today's lecture, in general, is embedded in computer mathematics, and computers are fine. Starting from Excel to specialized programs cope with this. The task of our course is only to understand the events taking place, so that when you work with a computer, you do not blindly look at it, but understand what is happening inside the computer. Why do you need to understand this? In order to correctly interpret the results that this computer gives out and which these scientists then publish. We look at the motivators. Yes, we publish in our scientific articles, and doctors read these scientific articles. Well, this is a separate conversation in our motivators on this topic. So then what? Well, by the way, this is the so-called two-way criterion. In fact, we are investigating. In our case, we investigated only the probability of increased diuresis. Yes, we investigated the process one-sidedly. But there are tasks when you need to investigate the deviation of a certain parameter, both in one direction and in the other, right? Just check that the parameter is changing. And then we use the so-called two-way. We divide this area in half, these two small ones, and we have getting here is perceived as a mistake. And getting here is perceived as a mistake. This is the so-called two-way criterion, that is, the study of differences in the subjects of deviation in one direction and in the other. So, another figure is quite complicated, but I have to show it to you anyway for the particularly inquisitive. This ratio, this is why this picture shows why we can't make the error equal to 0. Here is the error of the first one. Here are two hypotheses. These are two hypotheses. Let's test, let's say 0 and alternative, right? So we take and measure all the area for the error of the first kind. But here it is very big, taken, of course. Look, and as soon as we then, but on another hypothesis, here is an error of the second kind, that is, an error of the second kind is to accept an incorrect hypothesis. Here it is located here. As soon as we start shifting, reducing the error of the first kind, shifting this decision line here, we automatically increase the error of the second kind. Once again, trying to reduce the error of the first kind, setting ourselves the task of doing and minimally. We will automatically increase the opposite error. That's what the problem is. You can't. And 0. And the error is equal to 0 here, right? When the error is of the second kind, it seems to you that you have made a mistake of the first kind equal to 0. At this time the error of the second kind has become the maximum. That is, by reducing the probability of a correct hypothesis, you extremely increase the probability of accepting an incorrect one. That's all. Here in this figure is the so-called criterion power. We demonstrate why it is necessary to look for a balance between these errors. Well, okay, this is a little more complicated stuff. We're going to move on easier. So the criterion. We are with you the criteria of many different authors. We will still be the most, well, let's assume that it's not that common, but the most well-known criterion. It's the most accessible in explanation. We use it in practical classes. Although it is not always possible to use it, especially in biomedical research. There are some restrictions there on him now, he will say. Those student criteria, we call them. This is a series of metas of statistical verification and evaluation based on comparison with the student's performance. Their several criteria are really different in different ways of comparing using, yes, but they all use the so-called student distribution. This graph here is the distribution of the student, on the basis of which a decision is made to reject or accept the hypothesis. But most often we will also use these criteria to check the equality of two average values in two groups. Here you remember, yes, the same Duras, yes, that Duras is actually there in two groups equal and the drug respectively. Well, this is the null hypothesis. The hypothesis that the average value in one group is equal to the average in the other. But we have already discussed the null hypothesis. That's what the STU criterion is designed for. So, a little bit of historical information. William Shelley Goffett is actually the last name of his life. So, he developed this criterion for, while doing statistical research, evaluating the quality of Dine's beer. But note that this work was so important that he had obligations to the company about non-disclosure of trade secrets, and releasing his article according to the method of analysis, not about beer, but exactly about this proposed comparison method, yes. He put it up in the Biometrics magazine under a pseudonym. Well, the student called himself, and somehow it's gone since then, right? So, here are the restrictions right away. The most important thing that will limit this method. To apply this criterion, it is necessary that the initial data have a normal distribution. We discussed it quite simply. Unfortunately, experimental data, especially with a small number of trials in the biology of medicine, very rarely have a normal distribution, especially with small volumes of samples. These are already proven options, as it were, by experience. Unfortunately, it's hard to use it in practice, but it's very useful and simple to understand what's going on, to understand how the criteria work on it. Therefore, perhaps the most common criterion. So, the stages of hypothesis testing. Now we will go through the stages. So, it means that we are discussing the student's criteria now, yes, for his example. A clinical scientific hypothesis is formulated. What is it? We said the hypothesis that there is a drug that is effective for increasing diuresis, yes, in certain groups of patients. The characterizing parameter of the research is selected. But in those examples, since I'm talking about diuresis, yes, this is the amount of daily urine excretion, called diuresis. So it will be a parameter, right? So the statistical parameters of this study means the statistical third point of the statistical hypothesis will sound ah. So how is it with us? Unfortunately, I didn't write it down here. The hypothesis that the average diuresis in the group taking the drug is greater than the average diuresis. Remember the pictures there, yes, in the placebo group. Already there is that, well, let's call it 2. Suppose the group taking the drug is more than M1 in the group taking the placid. The hypothesis that the average value of diuresis is average, once again, all patients are different. The average value of diuresis in the group taking the drug is greater than the average value of diuresis in the group taking a placebo. This is what we formulated point 3, and, in principle, we should write down and the colon M there means, well. There we will have an example further, I will already show it there. For now, we are just going through the points. So we choose alternative hypotheses, of course, based on erroneous phenomena and their consequences. We analyze the situation and think, what should we oppose? Of course, we can counter the hypothesis that the average diuresis in the group taking the drug is less than in the placenta group. Well, it is possible. It is possible to contrast the hypothesis with a sign more with a sign less. But according to the meaning of the research task, well, there is no such thing. After all, we will take the null hypothesis as an alternative. It is easier to work with it, and it is more correct here. It will be less cumbersome that the average diuresis in these groups is different. There will be an alternative one, yes, but we also recorded it in the previous examples. So now let's talk about the so-called significance level. Now we are the 5th point we define ourselves. The next stage of the study is to choose the level of significance. And we will discuss this problem a little bit in more detail about the level of significance on the next slide. These are the stages, yes, I remind you again, so explained with diuresis, we are going through these stages. What is the level of significance? The level of significance is the very permissible error of the first kind. It's not just the probability of making it. It's the probability that we can afford. Once again, a mistake is always made. We have to determine a certain maximum error that we can afford. And if our experiment gives us a result less than this error, then we will allow ourselves, right? Well, let's do it for now. In biomedical research, this figure is most often used here, 5/100ths, or if it is customary as a percentage. It is 5%. That's how a person came up with such an emotional idea for himself, that here is an error of more than 5%. Well, ask you which error is big, which is small. Well, and everyone will basically come to the conclusion that more than 5% is already a Bolshevik one. But I will still tolerate less than 5, but there. Well, this is some kind of emotional, it's not an approved figure in any way, it's just, well, practically. Although there are some calculations and attempts to approve it there. Approve, why exactly 5%? Well, there are a lot of disputes on this topic and so on. Well, somehow it has been accepted for a long time that this limit, let's say, is 5% error. I say again, there are a lot of disputes in literature now. What kind of mistake should I allow myself? Often the question arises. So what does the error depend on? In fact, it's not always 5%. The permissible degree of risk of making a mistake in decision-making depends on the practical importance of the consequences of making this mistake. Let's look at what the consequences are, since we are hooked on this doer, yes, this drug here. A study of a drug that increases diur. Well, suppose we hypothesized that it is effective, and I'm sorry, as a result of the experiment. The null hypothesis turned out to be true, so the main one is not true and that's it. And as a result of the verification experiment, we came to the conclusion that a yes, no, it seems not so. Let's not. After all, we will make it put forward so that I am simpler after all. So, we put forward that it is effective, and as a result of the experiment, we did it. The experiment confirmed it, right? That is, but in fact the drug was ineffective, so the experiment developed. We made a mistake. In other words, we made a mistake. We made a mistake of the first kind as a result of the experiment. Which means we rejected the null hypothesis, accepted the hypothesis about the effectiveness of the drug, and mistakenly considered it effective. And he was actually ineffective at the general age. How do you see the consequences of such an acceptance? We are starting to put this drug into production. We are starting to prescribe it to patients. And only after some time, both patients and we, as doctors, are convinced of its ineffectiveness in practice, too. Having spent some money, having spent their money and taxpayers and patients from someone, having spent time, having brought some suffering to patients, well, not tragic, but of various kinds, and so on. In other words, here is the economy, such emotional consequences, as it were. In general, it is also unpleasant, but, let's say, not tragic consequences. Therefore, for such an experiment, which we have 5%, it will be normal. Yes, but if we, for example, tested a certain drug for anesthesia, yes, it means that if we experienced that. So, if you and I are going to experience some, well, a more complex medicinal form there, more critically affecting the functions of the body. Yes, well, drugs for anesthesia, I conditionally call it that. Yes. And we will also accept the false hypothesis of effectiveness and begin to give it to patients to use for such more critical situations, which can lead, to the death of the patient and more severe consequences. And we have to ask ourselves these kind of experiments, a smaller one, but 1%, for example, somewhere 0.1%. We are forced to manipulate the allowable error or the significance level is less than 5%. In other words, you understand that the choice of the margin of error is determined after analyzing the consequences. So I basically told the truth and I won't go any further. It means a number. It is important that in the future, we will still need such a concept as the number of degrees of freedom. We talked a lot in the first classes and lectures about what is important in statistics is the number of patients, but everything depends not on the number, but on a certain concept of the number of independent data elements that can change, vary. This is a difficult question for people with no mathematical education, right? Here it is very simple. The number of degrees of freedom, if the number of people in the group -1 is equal for one group. But for two groups, if we compare here in this situation, then this is the first group -1, the second. Oh, I'm sorry, I'm a little typo here, the second one is also -1. And 1 - 1 to -1. That is, the sum of my -2. I described this here in a confused way. Here too, the unit h is 1 - 1, to -1 there. So, look what. So, for example, you will try to back it up with a simple example. For example, he is a little bit to the side like this, but nevertheless he shows well. Look, if we decided to interact with patients, describing their condition in two categories, it means that pain is healthy. And so all the patients come, we say, this is healthy from pain. From the pain, right? Here in such a system of two coordinates, as it were, the number of degrees of freedom, think about it, will be equal to what? The patient can change his condition how many times? That is, the patient's ability to vary is limited to 1. He being healthy can become sick, and being sick can become healthy. That is, the number of variations, possible changes in such a system, is equal to the number of states minus 1. That is, 2 minus 1 equals 1 yes. Well, if someone didn't understand, I'll complicate the situation. We decided to describe patients in 3 situations. So good, satisfactory, and bad, right? So 3 yes, we did. In this situation, the patient has the opportunity to change twice. That is, being in good condition, it can become satisfactory, bad, and being there, for example, in bad. It can become good there, well in general. That is, the number of changes is equal to the number of states of the system minus 1. But when we examine 2 groups, this is how we proceed from the first group, we subtract the units, and the second unit again. Colleagues, I apologize for the imprint. There should still be a unit here. Yes, let me even try to correct it. So here's a 1 instead of a 2, right? I somehow had these 2 in mind, and that means I wrote a little, I made a typo. So it means the 6th stage. That's why we need this number of degrees of freedom, and therefore we need to complete the 6th stage. So that according to the table. This table corresponds to the graph that was seen. It's just difficult to work according to the schedule, so we work according to the table. So we need to determine the so-called critical value criterion from the table. We take the number of degrees of freedom. Here, for example, we have here on a task for almost 58 there, we get 30 people minus 1 plus. In the second group, 2, 30 minus 1, 29, 58. And here we are using this figure, for example, practically. So then, the acceptable error level we have chosen is 5%, or it is 1%, or it is 0.1%. But we are talking about 5%, and at the intersection, we find this number, yes. 58 is the number of degrees of freedom, and the critical value is equal to no one conditional to understand. 2 whole 2,000ths can be removed by 2 deuces. At the 6th stage, we determined the permissible error, determined the critical level of significance. The number of degrees of freedom, and extracted this number from the table, the critical value of the criterion. So what do we do next? Then we calculate the so-called actual or observed value of the criterion. We calculate in such a simple formula the difference of the average values, taken modulo to remove the sign. And such a sum of the squares of the errors of the average value. I remind you the error of the average value is the mean square deviation, divided by the root of the number in the sample value. We have already calculated this arithmetic mean error at previous stages, so-called I will not repeat it about it. We calculated it very simply too. This is the scatter standard deviation, divided by the number of people in this sample. Using such a simple formula, we substitute experimental data into it, and calculate another value of the criterion. The so-called t-observed value, right? So we calculated it, so we have this critical 2 and t-observable. So what do we do next? Here we are not calculating now, we do not have experimental data, but we will give the next one. Stage 8. We compare the critical observe. If the observed value is greater than the critical one, that is, it falls on that graph. The observed more critical one falls into our experiment in the blue area. What is the t-observable more critical? Here there is a critical one that limits this error area on average. And if the observability becomes greater, that is, our experiment falls into this blue triangle of 5%, yes. Then what do? We reject the null hypothesis as well. If you are more critical in the observable, but we have to reject the null hypothesis. Which means that if our observable is less critical, we accept it, we do not reject it, as it says here. So, suppose we rejected the null hypothesis about the equality of diuresis in groups. Let's move on to the next stage. The main one is rejected or accepted. If we rejected the 0,1 at the previous stage, then we accept the main one. If we have not rejected the null hypothesis or accepted the null hypothesis of equality, then we are forced to reject the main one about the effectiveness of the drug, right? We recall the beginning of the reasoning of the relation of the hypothesis there. Well, a certain conclusion is made in relation to this clinical hypothesis. Which means, the conclusion. Let me be quick. I have such a kind of example, now I'm even ready to run quickly. If it's really fast, then we don't have time for it. An example with numbers already. It is necessary to evaluate the treatment with a new antibiotic. We take two independent groups, small, unfortunately, groups of 8 and 10 people. Controlled temperature study parameters, right? We will measure the temperature of patients who receive antibiotics. The statistical parameter is the average temperature value. In other words, we will compare the average value in these two groups. So, the main hypothesis. The hypothesis that the temperature in the first group is greater than the temperature in the second. The second one is the one who took the antibiotic, the first one, which is not, yes, it means. So the hypothesis is that the temperature where you were not taken, on average, is higher for you than in the one that took these. The alternative is that it is zero in that the temperature does not actually change under the influence of antibiotics. We choose the criteria because of the simplicity we have already said. Select the significance level. The 5 yellows also explained everything. According to the table, it finds a critical value, so criterion n1 plus n2 minus 2 is this formula, right? 16.8 plus 10.18 minus 2.16. We find it in the table. Unfortunately, we don't have it in that example, in the table. We find those critical equals for, that's right. Note that the smaller the number of degrees of freedom, the higher the critical value. It is more difficult to exceed it for proof. So we calculate the calculated 1, but for a second, for 0.2, the calculated observed for 27, yes. According to the formula, let's assume n counted. We compare the observed critical. The observed is more than a little bit, it is more critical for 27. Is more than 405. And we reject the null hypothesis. We accept an alternative hypothesis. I remind you, it looked like that the temperature in the first group was higher than in the second, taking an antibiotic, which corresponds to the scientific hypothesis of reliable differences in the effectiveness of the new drug and the placenta. Well, that is, the drug is effective. And we write the conclusion. As a result of the experiment, it was possible to reliably confirm the effectiveness of the new drug, with an error probability of 5%. That's it, colleagues. Let's take a break for a short 5 minutes and continue on. Dear colleagues, we continue our lecture, the second part of it. And unfortunately, we have a compressed lecture. It consists of two large topics, so I probably hurried in the first part, yes, in order to accommodate two important topics. So the second topic is that it also includes a method that is important in medical research, in clinical research. But on the other hand, it allows us to evaluate certain biological processes in the patient's body. But now we will explain this. And this part of the topic is called correlation analysis. So, well, let's take a closer look at the correlation in Latin. This is the relationship. So, the task is to identify the relationship. Well, here's a little messy identification between phenomena, but nevertheless. The task of correlation analysis is to identify the relationship between two random variables from the point of view of mathematics. Who acts as these random variables in medicine? What relationships do we have the opportunity and are interesting for us to identify in medicine? So, the first kind, and I'll even say right away that this kind of relationship means that we have a diagnostic orientation. So it means that this kind of relationship carries a clinical direction study, right? Well, I'll explain now. So the first type of establishing dependence or relationship between different indicators of the body. In other words, a lot of indicators are examined in the patient's body. We can often look for relationships between them on the surface, interpret them in some way, think about what is happening inside the body. That is, by examining the interrelationships of the sign of available signs, most often from the surface. Or from a small depth, of the organism, yes, we are, available to us for the study of signs. We can build, knowing their interrelationships, build reasoning about some deep processes in the body. Second, what is the treatment? It consists in the influence of some external, right? And we can, by examining the body's reaction to this, to the dose of exposure, yes, to the strength of the impact. We can also talk about how the body reacts and what happens there in the body as a result of some kind of therapeutic effect. Yes, like this. Diagnostic and therapeutic tasks are both solved through the analysis of the relationship. The method for analyzing the relationship mathematically or statistically is correlation analysis. So let me try to explain it more broadly. And in order to explain this, I didn't even draw it just at one of the classes on the blackboard. Somehow I got drawings quite successfully. I'm just going to reproduce these drawings with chalk from the blackboard at one of our classes with students. So, as we said, look, this wave here is the surface of the body. That's what's here, it's inside the body, yes, it is. So there is, for example, an inflammatory process going on inside the body, right? So it is reflected in what? As a result, it is reflected in an increase in body temperature on the surface and in an increase in blood. But of course it is a bit wrong to say on the surface, but nevertheless. We take blood and measure the number of leukocytes in the general analysis. That is, as a result of the inflammatory process on the surface, but the conditional surface of the body, yes. The temperature rises, and at the same time, the number of white blood cells increases. In other words, these two percentages are interrelated. How are they back? As soon as the inflammatory process begins to subside, the temperature decreases, and at the same time, the number of white blood cells decreases. That's what a relationship is when two processes behave the same way. When one increases, another indicator increases, and when one decreases, another decreases. And the weaving on the surface of the factors available to us, yes, gives the doctor, and the doctor knows about this relationship. It was established by someone a long time ago in some experiments and entered already in the textbook, yes, that is. This relationship is already an element of the textbook, but it did not just get there. It was the result of some experimental studies confirming this relationship. It has already been confirmed in the doctor's head, so it is being entered. And the doctor, if he sees this relationship on the surface, sees it, observes it himself, then he says yes, then. Most likely the cause of the processes occurring is inflammation. But look what will happen in the doctor's head if the connection disappears, if the temperature rises. And the white blood cells do not respond. What is it? This is the disappearance of the relationship. This is desynchronization. This is a process. Why did the patient's temperature begin to rise while the white blood cells did not increase? This encourages the doctor to think in the other direction. Well, for example, there are some pathological processes that enhance metabolism, we will not argue. As a result, the temperature rises, but it did not affect the white blood cells. He starts looking for these processes. Well, here's the diagnosis, yes, but it was born, so to speak, an incentive to look for him because of the loss of the relationship. A known relationship disappeared. So we will consider the other side of the process. And if the leukocytes began to change in the smaller direction of leukopenia, for example, decrease, and the temperature does not change the body, and this is an occasion for the doctor to think about even more complex problems, for example, oncological pathology of some kind, yes, it means about more severe, yes, the causes of such a process, for example, a decrease in white blood cells and at a stable temperature. That is, the connection disappears if one changes and the other does not. It's a disappearance, a relationship. And we observe all this in the analysis, on the surface of the body, and so on. But we are looking at this connection. We are at this relationship of to blood, and there is a body there. But this is also blood a little bit, only in a different expression of body temperature, right? We begin to make sense of something somehow, knowing the relationships, and thinking something about the body. Here is the first diagnostic. Yes, the use of the relationship in the doctor's head is something to scroll through. So then what? So the second part is about the therapeutic part. The inflammatory process inside the body. Naturally, it is expressed by an increase in temperatures. We give the patient a different dose, well, from 10 to 100 milligrams of some kind of antibiotic conditionally, right? And we observe the relationship, all the more dose, the lower the temperature. Yes, there is such an inverse relationship, but we will now say yes, direct. Nevertheless, if we see the reaction of temperature changes when the dose changes, that is, this relationship. The dose in numbers, the temperature is expressed in figures of two quantitative indicators, then we say, yes, the drug works. The drug is effective to wash. Observing the relationship, we come to the conclusion about the effectiveness of medical procedures, right? Not just about efficiency, there's also a general one, this is my favorite experimental one. In this way, by observing the relationship, we can choose the most optimal dose on the one at which this relationship is most pronounced. Right? Here's another valuable thing, we can choose the best dose from 10 to 100, yes, for the treatment of this inflammatory process. But we are also here with this double arrow, I will depict the relationship. Here it is, this relationship is formed in experiments, something else is calculated, but this relationship lives in the doctor's feed. It gets into textbooks, and gets into the doctor's head, and is used by him subconsciously, yes, for diagnosis, and for treatment. But at the heart of everything are the interrelationships of these processes, and those listed there. So let's define correlations. Correlation relationship or correlations is a statistical relationship between conditional random variables x and y, in which each value of a certain value x corresponds to not one specific value y, then it would be called functional. But its group average. Well, for example, x, let's take the age, yes, the value of the first sign. Y is the value of the second sign, blood pressure. Here it is written finely P arterial. And what do we get? That the same age corresponds to a whole set of Y1, Y2, Y3 completely different blood pressures. But nevertheless, this does not mean that they are not connected. Nevertheless, we know that as the average age increases, the average pressure of a group of people over the age will increase. That is, nevertheless, there is a connection between age and average pressure. We all know about it that older people have higher blood pressure on average than young people, yes, on average again the chest. This relationship of one trait with the average value of the other will be, in general, a correlation. Yes, this is demonstrated here. This is a mathematical expression of a functional relationship, a kind of formula, yes, or functions. When we substitute a certain value into this function, we find out the exact value of the games. But in medicine, these are impossible functional connections. We are forced to advance the coalition. We establish a certain relationship between the value of the x of a certain indicator of the body or a dose of a drug, with a certain average value of the same temperature, a certain dose of the drug, and the average temperature value when taking such a dose. Yes, it is clear that the temperature will be different, but the higher the dose, the lower the average temperature value. Relatively speaking, x with a y, here I have given examples, this is the dose of the drug and the average temperature value. Here is a functional relationship, a coalition relationship. So, well, let's take it in some forms. So it's a little early in strength, it's not explained, but nevertheless, now we will show it. First of all, we evaluate the strength of the so-called strong, medium, weak connection. The simplest estimate is as follows. Well, first of all, we evaluate the strength of the connection. So, second of all, we evaluate the form of communication. The relationship can be linear or non-linear. So let's look at the graph about him a little later. This is a graph depending on a certain value of x. Again, that we have me there at an experimental age, right? And why blood pressure? Look, each point is one patient. That is, this patient has elderly patients, these are young patients, right? Note that the higher the age, the higher the blood pressure. The pattern can be traced, but nevertheless, the pressure fluctuates this process. But we are his, each point is one patient. This means that we nevertheless build the line closest to all points, called a trend or geometric trends, which is the closest. And it is along this line that we evaluate, which means that we consider this line to be correspondingly close to linear, not absolutely linear. But at the same time, we can observe other processes where these points corresponding to patients will be located along some kind of tricky curve, right? These are more complex processes, we don't even use it in our analysis. Because these are very complex methods for evaluating nonlinear interactions. And it is also not quite correct to use a linear one to evaluate such dependencies, because if we draw a line here, you understand, it will not express anything. That is, in such a complex dependence on one trait from another. Well, that is, we just remember that there is a linear-nonlinear dependence. But for simplicity we will use only linear relationships, which is not always true again, right? In the direction of the relationship there are direct and inverse. An increase is about to show a direct relationship. An increase in one sign of an increase in age leads to an increase in pressure. And an inclination of the curve like this, yes, so here it is a direct relationship. Or it is also synonymous with its positive correlation. Direct or positive. Accordingly, an increase, if one sign of age, gives a decrease, but here I do not know what. I do not know. It is difficult to say what the working capacity of muscle strength is. Suppose, yes, there is muscle strength, yes. An increase in age will lead to a decrease in muscle strength. But again, this is also a nonlinear process of some kind, but nevertheless, yes, we call this relationship inversely. Yes. Here are two graphs of a direct inverse relationship. Now we have asked again, so we will talk here a little bit like this, we need to repeat the slides. So the slides need to be repeated. Means the ways of setting the correlation relationship. So, how to write it down if we can't? The formula doesn't suit us. You can't create a formula. The formula is only suitable for functional relationships. The first form is a correction series. It's just that a table is compiled where certain fixed values of x are entered, and in an experiment, averages are calculated in certain groups of patients, and yes. Here I won't even say what kind of experiment it is because it's difficult to get to these figures. But nevertheless, you can already see from this plate that this is an inverse relationship. X grows, Y decreases. Some kind of inverse relationship is formulated. According to the table, it is difficult to judge the strength of the connection, because it is a cumbersome design. But nevertheless it will fully evaluate the connection, but it is difficult to manipulate and use for some conclusions. It is very cumbersome representation, but we need it. We are starting with this at the beginning. Here we can express the relationship with such a table or a so-called coordination series. It's a series of values, right? It means the first sign and the average value of the corresponding other sign. It expresses it accurately enough, but it is cumbersome. So, the second form of determining the connection. So we have already started working with it, but have not yet explained it. The so-called scatter plot with a regression line. Or another synonym about regression. We will not use this term trend line later, we have already said. Yes, this is really a regression line, but we are going to use this word. We have a separate section of today's lecture about regression there. This means a chart with a regression line, or a trend line. On the axis of the abscissa, that is, on the axis horizontally, the first sign that we had growth is postponed. Oh, age, I'm sorry, right? And along the ordinate axis, or the vertical value of the second, for example, there is blood pressure. And so we have some points of these patients, we are trying to circle them, yes, so we are trying to build a kind of regression line. And a trend line like. Note how this one differs, for example, depending on the previous ones, yes, then that the points are closer here. And now we immediately see that this connection is strong here, the closer the points are to the line. The stronger the connection between, again, I forget age and blood pressure. This strong positive one is depicted, yes, but they are all linear. Oh, strong direct connection, right. Direct strong connection. This is a strong feedback. The points are also close. So this graph shows a direct connection of average strength because the points are already further away, yes, graphically. And here is a picture of a situation with a lack of communication. When the dots are located with this dot, it's once again, each is a separate patient. The points are arranged in the form of a circle, and it is no longer possible to draw a certain straight line through the circle as you like. It is impossible to find a trend, that is, the line that determines the course of the process. There is no situation when the points have completely moved away from the center and turned into something like a circle. Yes, you have formed? We tried to circle this with a kind of dotted line. Once again, I repeat, so here are the characteristics. This is a strong direct connection, judging by the graphs. This is a strong feedback. This is a medium-strength direct connection. And this is a lack of communication, right? Well, that's all good. These are the rows, so they depict the graphs quite beautifully and clearly, but they are bulky. And we have to deal in clinical trials with not one, but with many relationships. And it's very cumbersome and unproductive to express 24 connections in one study, with so many graphs and tables of these there. Therefore, we use the so-called linear correlation coefficient for more massive changes. The letter P denotes a certain numerical value that simultaneously demonstrates the strength and direction of correlation relationships. Even for quantities in units, in different units of measurement. Yes, we have already said this, giving an example between the temperature of white blood cells. If in the previous section of the lecture, where we compared groups, we were obliged to examine the diurist in one group of patients, and the same diurist in the other in those reapers, and compare two identical values. The other one. This method doesn't work any other way. Yes, hypotheses. When we test hypotheses, then here we can compare absolutely different quantities. The only requirement is that they are quantifiable, right? And one more limiting requirement, but it's not any correlation coefficient. We said, here we are going to talk about correlation coefficients now. There are different methods according to the authors who determined them. The most famous Pearson correlation coefficient. Here we are here about its characteristics, we take restrictions. It is again, like the student's criterion, the simplest, widely used, but again limited by the same normality of the distribution. And there are other rank correlation criteria that we have. That is, the absence is normal. They are weaker, but they allow us to investigate processes that are abnormally distributed. Again, I'm already referring to the previous lectures, right? So, nevertheless, we are going to discuss here, for simplicity, the Pearson-Ruler correlation coefficient. The Pearce linear correlation coefficient. And it requires quantitative features, and it requires normality of distribution. I must say right away, there are statistics and methods that do not evaluate quantitative signs. Well, for example, relatively speaking, smoking is a sign, for example, there is such a smoking is not smoking. Yes, this is clearly not a quantitative binary feature. You can compare it with age with what? That is, it is possible in principle, I won't even go into details now. It is possible to have methods that compare non-quantitative features, but we are not talking about them today. So we have limited ourselves to this linear correlation. So, what is it? But we will nevertheless talk about the properties of this P correlation coefficient, but nevertheless. An extremely convenient compact method for assessing the relationship, I remind you. So, well, we have already said, as it were, that linear correlation acts according to a linear law. It's like a kind of chewing again, but what is it? What is a linear relationship? That here is the correlation coefficient that we use for the samples. It is suitable only if the relationship is linear. There are also many restrictions, of course, introduced, but nevertheless forced to work like this for forgiveness. Let's look at what properties this correlation coefficient has. So, it means the value, you have already talked about it, the value of the correlation coefficient does not depend on the units of measurement of quantities. You can grow with weight, or with temperature, anything with anything fear. We have a different comparison task. We are investigating the synchronicity of processes. We are investigating how much two processes behave as if a change in one indicator is synchronized with a change in the other. But it can be synchronized in a positive way, that is, an increase in one, an increase in the other, or in opposite directions. This is a feedback when an increase in one leads to a decrease in the other. But nevertheless, we are no longer interested in the units of measurement here. The value of the correlation coefficient is in the range from -1 to +1. So, if the correlation coefficient is 0, then this is the situation. Sorry. If the correlation coefficient p is this after calculation. By the way, here the methodology is simpler than the criteria of the competitor. Here is this correlation coefficient of Pierce. It is calculated using only one formula. No tables are needed, no comparisons are needed. There is also a formula that is not bulky enough, compact, substituting experimental data into it. You can get here a certain number in the range from -1 to 1, and then start evaluating it. So, if the correlation coefficient is less than 0, if the number is negative, then the correlation is inverse. A negative sign indicates that the correlation is reversed. I remind you, there was already a schedule, that the schedule would tilt her like this. As one attribute increases, the other decreases. Here we had an inverse correlation between the dose of the drug and the number and temperature. The higher the dose of the drug, the lower the temperature, right? If the number is calculated to be greater than 0, then the correlation is approx. In other words, we had a correlation between temperature and white blood cells. The higher the temperature, the higher the number of white blood cells. It is clear that this reason is the inflammatory process. This is an example of a direct correlation, right? If p is 0, then there is no connection, yes, but there are no such situations either. This is usually some kind of extreme case. If p is equal to 1, then the correlation relationship turns into functionally. That is, if there is a connection, that is, it is a kind of absolute connection, and, accordingly, it becomes functional. It can already be expressed with a formula. But this also does not happen in the biology of medicine. There are practically no functional connections here. They are all relational in one way or another. Here are some properties or values of the coefficient. This is a number from -1 to 1, if the minus sign. But once again, minus in strength, it means a second. But now he asked further, yes, I'm probably running ahead. So, that is, the number itself carries the strength of the connection, and the sign carries the direction of the connection. That's what we're talking about, right? Because -1 and +1 are the same force, but in a different direction. Here's what else. -1 is not less than 1. These are different directions of communication. So let's talk about the so-called verbal correlation coefficient scale. An attempt to turn the force into a kind of description. And a certain scale. There are many scales, but let's consider one of the scales. And note, the value of the correlation coefficient modulo. We have removed the sign, it is not important to us for strength. If we remove the sign, then we can evaluate the power. Strong or close connection, the correlation coefficient is greater than 0.7. Once again without a sign. The average is from 0.5 to 0.7, which means an average connection. We'll call it average somewhere and we'll interpret it that way. Weak connection from 0.3 to 0.49. Well, we have no right to talk about the lack of communication at all. We have the right to call all connections less than 0 as many as 3/10 of the correlation coefficient very weak, and, as it were, exclude them from our reasoning and so on. But to state that with a correlation coefficient of less than 3, it is absent. Impossible in medicine. These are statistics. You can't reason like that here. The verbal scale doesn't provide for that, does it? It provides for the absence of communication only at 0, and 0 does not exist. That's what it's about, right? Just like this strong connection, it will never turn into a unit. Well, here is a kind of verbal scale, which in these very same, we apply to medical articles. That is, when you conducted an experiment, calculated the relationships, entered them in a table. And then you need to interpret. You need to select strong connections, explain their reasons, search, explain, interpret something somehow, yes. The actions are drugs, or is it an inflammatory process there, something else, yes. And then you start using the verbal scale, or you are not the author of this scientific and medical article. And it means to describe somehow when describing the connection. This verbal scale is used in the description, right? Actually, it's a number and only, yes, but it's unsigned. The sign says a plus after all. Direct communication, minus the reverse. What is it? We've already sort of explained it, right? So, come on, let's move on. So now there are important things. Yes, look, here is the important thing. Math, statistical work is over. You conducted an experiment, got a set of numbers, leukocytes, a number, a certain number of numbers. A certain number of numbers, or we have already given an example of the dose of the drug there and the temperature, yes. Substituted it all into the formula of the correlation coefficient, but somehow I did not give it. It is quite simple. Not the point is not in it, yeah. In practice, work is also for practical classes. We set up a formula, counted a certain one number, and just one number is a sufficiently necessary process. They looked at his sign, looked at the value, translated it into a verbal scale. That's it. Now you have to remember these drawings. Let me go back to them, right? Now you have to imagine in your head the anatomy, physiology. Where is this, right? Imagine this is your knowledge about the human body. That's it, math won't help you anymore. Math will end. She wrote here p equals 0.8. Or here p is equal to minus 0 as much as 75/100 minus immediately negative. We said the opposite to put a multi here. For example, here p turned out to be plus 0.8 and here p minus 0.75. Yes, that's it. In order to use this further and already talk about the effect of the drug or about the processes taking place in the body, you need to connect other sciences. The math connection only made you do it. It can show the strength of the connection and motivate you with medium or strong connections. And sometimes even weak connections discovered if they are rediscovered. Motivate you to think in other areas. Physiology, some clinical disciplines, that is, to connect the knowledge of other disciplines. Now I'm coming back from here, yes, these properties. Look here, correlation does not establish dependencies. It is a measure of the joint variation of two features. She does not talk about any dependencies, about any inflammation of the correlation. She doesn't care, she doesn't know what mathematics is, what inflammation is. And inflammation about these causes, about oncology or metabolism, or about the dose of the drug, you should reason based on physiology, pathology and other areas, so your accumulated knowledge, yes, medical. Here's what again. Never ask for explanations from the computer. The computer is not meant for explanations. Oh, or this math implemented on a computer, yes, statistics. Statistics don't explain anything. It provides material for reasoning and for reflection. You use physiology, pathology, clinical disciplines, and so on to reflect. Statistics only motivate you. That is, the discovery of a certain connection motivates you to go deep into the body and look for the causality of these connections. That's what this slide says, this note, right? For each of their own mathematics and numbers for other disciplines, this pathogenesis is there and theology and so on, right? And already the reasons for the connection you should look for yourself using other knowledge. This is an important, by the way, very important note. When you write, for example, I am interested in the conclusion there, well, in some practical work. You start there, the correlation tells us about there. The correlation doesn't tell us anything. Correlation is a measure of feature variation. That's it. And already where did this variation come from? It's right here with this. Okay, I repeat this a lot, so, well, this is what I've probably said a lot about. This is what I showed there, the interrelation of signs. This is once again about the usefulness, yes, of this method. Quantitative detection of dependence can be useful for understanding the relationship between biological processes. Here we are the process of inflammation. Yes, to understand it, we analyzed it. And the prediction of their mutual behavior and consciousness and the creation of indirect diagnostic criteria. But here's a separate one about indirect diagnostic criteria. Look, we're actually even body temperature. So we really love this key indicator of body temperature. After all, this is an indirect diagnostic criterion. It is an indirect diagnostic criterion of that internal inflammatory process. He's a body temperature by himself, nothing. This is a kind of superficial indirect value associated with the inflammatory process. And we, knowing this connection, are not really connected with the temperature of white blood cells. Yes, let me come back here again. It's really far to run. In fact, it's not the temperature that is associated with white blood cells. In fact, temperature is associated with inflammation, and white blood cells are associated with inflammation. But this relationship, it is not indirect. This is a consequence of these two connections. In fact, there are two connections. Increased inflammation increases white blood cells, a direct connection, and increased inflammation increases the temperature is also direct. In fact, there are two in the body, but we do not see this process, it is deep. We see on the surface an indirect expression of these two connections merged, expressed in one indirect connection. This connection is indirect. They actually do not heat up the body with each other, but understand that if an increase in white blood cells warmed up the body, and their number led to an increase, it would be a direct connection. In other words, this relationship is indirect, and it expresses the presence of two direct relationships within the body. Inflammation of white blood cells, and this inflammation is for you. This is about indirectly. This is a conversation about what is given there. It is given there under the word indirect, yes, relationships. 1 second, I ran far. Yes, not an indirect diagnosis. This is an indirect diagnostic criterion. But we, on the surface, are forced to manipulate indirect relationships and think about those deep relationships. All, perhaps, here is a correlation analysis, but we are not finished. We are doing it, we are continuing it, but in some deeper expression, it is a regression analysis, the so-called regression analysis. The same graph here is about the same thing, but in a more, let's say, wider and deeper use of this method. Now I will mark what it means that the correlation coefficient is the basis of correlation analysis. In other words, we are the product of correlation analysis is one number, which, by one digit, and by its sign, and by increase, allows us to talk about the strength of the connection and the direction of the connection. Everything seems to be fine, very compact, convenient, and so on. But not everything speaks about the process. We want to know more about the process, besides its strength and direction. We want to, so we are trying to turn it into a kind of regression analysis. We are trying to develop the same dependence a little bit. So, what is regression analysis? Regression analysis is a method of investigating the relationship between the variable y and one or more independent variables x, y. It's the same as last time, only here we can have several x's. So, y is our blood pressure, let me remind you, but there can certainly be one reason for blood pressure. That's 10 height, we say sorry, age, right. But in fact, there may be an age according to the diet there, I do not know, something else there is a lifestyle. There are still a lot of all sorts of parameters. In fact, it means that this sign of blood pressure has many influencing reasons. And they can all be expressed in terms of x1, x2, x, right. In other words, we have expanded the concept a little. There may be one dependency. If we take 1x as an independent variable, then we get the same correction 1, yes, it depends. But nevertheless, independent variables are very usefully called a predictor. And the dependent variables are the result or the answer, but here we will not be criteria-based. Well, here's a y. The y is often called even the regression response or the result. Well, notice here, a very useful predictor word. The predicate predicts it, yes, in English. There is already some hint of a prediction. So, once again, these are independent variables, y-dependent, and here they are called differently here. A little bit of this confusion takes away, we will not say it in subtleties. Let's see what the correlation coefficient means. Here it is again compared. The correlation coefficient only indicates the direction of the force in the connection, but does not make it possible to judge how they change. Does not give them the opportunity to really turn one into another, right? The correlation coefficient does not allow, even with the age value, to know at least the average even blood pressure. He's just saying how strongly connected they are. He does not give us the opportunity to turn one into the other. Here we are, as it were, trying to approximate the function. We are trying to build some kind of formula for this dependence in this case. Not just to talk about strength, but to build exactly the form. To get this dependency, we use metrycresty. This is essentially an attempt to improve the correlation coefficient and build a certain formula that will not just say how strongly age is related to blood pressure there, but also substituting a certain age into it. You can find out at least the average pressure for this age. And then compare a particular patient with this average. Where does the average age pressure come from, right? From a certain formula, yes, and the formula follows from, it is obtained by regression, yes, by regression analysis. Well, let's see how the formula works. What are we talking about? Let's remember about school geometry. We say that the basis of correlation, and, accordingly, regression is a line. This line was even called a trend line, or a regression line. The drawing is absolutely the same as it was. He expresses the same relationship, once again between age and blood pressure. Positive strong, direct or positive strong, and so on. So, how is the line formula written in geometry? Y equals A plus bx. That's the formula of the line, right? Where does it mean that the letter A means? If x is equal to 0, that is, if the age is equal to 0, then well, it's certainly ridiculous for the age there is 0. Well, conditionally, what is a person born with? Yes. What pressure does a person have at birth? Yes. Can be calculated along a different line? Yes. So if age is 0, then y equals A, right? That is on the graph. This is the point to which the line intersects the y-axis. Yes, it does not intersect with 0. It is a little bigger here. You see, when growing, it has some kind of pressure greater than 0, right? That is, and this is a certain coefficient showing what value y has when x is equal to 0. And what is b? B is the so-called slope coefficient. B is the slope coefficient at which, that is, it shows that the more b, the steeper this line goes. Yes. So, when it changes, if it decreases, then the slope of the line approaches x. If it increases, then the y grows faster, right? In other words, this is a kind of growth coefficient. This is the dependence coefficient. The proportionality coefficient between y and, yes. Or it's here for geometric, it's the slope coefficient. Well, it's just a formula from the geometry of the y, plus bx. Look, we take a set of experimental data, substitute them into a certain computer, or manually. But manually we are not talking about this, are we? And the computer gives us two coefficients as a result of its work. That is, we have how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19 patients. We substituted them into the equation. The computer revealed the dependence of this line to us and built a formula for this y plus line, right? And look, now we have a formula. Now we can put any value of any patient x of his age into this formula and find out what kind of pressure he should have. Well, roughly speaking, this pressure is normal, right? Notice how wonderful it is. We can predict, we can't even predict here. Look, if we mean one of the parameters, for example, is time, yes, if we examine the course of some process over time. And, by the way, it is. Pay attention, colleagues, this is the same age, what is it? It's a time parameter. He's already measured in years, right? That is, we have a lot of certain indicators that change, we are interested in over time, right? If we, for example, have time, then we can, roughly speaking, predict the future so provocatively. Knowing how a certain process behaves in the present, and constructing a formula, we can substitute the future time, yes, by measuring people at this age. Well, let's give a funny example. Here we know how people are now under pressure there, but conditionally, the example is rudely very funny and so on. And what pressure should a person at the age of 150 have? Well, this is a funny example, it's a nonlinear dependence there. In other words, we can predict certain future conditions of the patient with the help of this so-called regression model. Of course, it's hard to predict roughly, but nevertheless we have the opportunity both to recognize the increase in pressure with age and to predict it for the future. So this is in the simplest case. What does it look like in real life? In real life, of course, pressure is affected not only by age, but also by other parameters age. There is some kind of presence of some other quantitative signs, and I do not know, a lot of different signs, right? And we can include all of them in the model, here denoting 1 BCS2, X2 and so on. But we always don't take everything into account, so a certain ERF error is added to the formula, right? The formula takes into account that, nevertheless, the sum of these signs will still not give us the exact age. We will still have some kind of error, right? Well, once again, I have already said this, that the coefficients of the model are obtained by regression analysis, using experimental data, which make it possible to determine the average value of the desired one by attracting one or more features. Such a wonderful task for a doctor is to predict. In other words, the regression model is used for two tasks, for diagnosis tasks. In other words, we have to indirect 3 to 10 indirect signs. We can substitute them into a certain model created in advance, predict the state of something inside the body there. This will be a very useful diagnostic model. We have some indirect signs on the surface, and having a model created by someone in advance, we can predict the state of organs at this time inside there, right? And we can use a predictive model with a model. It's even more interesting, yes, when we, have a set of signs, genetic signs of some other, yes, substituting them for someone else, a model was created by someone else. This is the most practical tool model, regression modeling. Substituting these signs of a particular patient who came to you into this formula, predict the development of the disease for him. Predict some outcomes for him, predict something else for him. Very useful. It's basically, mind you, the same drawing, it's the same expression of the relationship. Just in a more advanced one, when we use the line not to measure it, just there is this force, the approximation to the line. But when we create this line formula, once again, the so-called one-factor regression, but this is very weak in practice, yes, because the pressure not only depends on age, but also depends on many other signs. And this multi-factor model is very useful precisely for practical reasons. Medical science is the most useful practical product for medicine of creating models based on experiments. Of creating this model, which a doctor can already use, and in his computer substitutes something for the patient's value there. Predicts something. In other words, here is a very useful development of the relationship in the form of regression analysis. But we don't have him here in the first year. In our second year there, in our computer statistics unit, there is a small amount of work there with regression tasks. And the students, of course, who are engaged in science here, they are more advanced there, and are engaged in solving experimental problems. So, well, colleagues, perhaps I've said everything I could though, and then very quickly, because once we had these two topics separately, when we had more time for this, we were allowed to teach this discipline. Now we have to combine them. Once again, these are two different topics. Once again, testing hypotheses and checking the relationship. But they cover, as it were, two main ones. There are other statistical methods, more subtle and more complex, used in medical science, but these are, perhaps, two basic methods of working with clinical medical research. And therefore, I say again, not because you will count them there on the calculator. The computer decides everything, there is it, and even Excel decides, it is a specialized program that decides. Your task is to understand what computers do. And only then will you be able to use. But I've tried to give you examples on leukocytes of a way of thinking, yes, a kind of statistical one. And through these relationships it's also connected, even without a computer, right? But nevertheless, you need to understand these two industries, understand this terminology for reading articles. Understand what is happening between biological processes, and understand their random nature, and how to use it, and so on. Well, in other words, I thank you again for your attention, and perhaps this is where we end our lecture.